So welcome back everybody to our radiation heat transfer learning journal. So in the last video, we're talking about part one of the radiation heat transfer analogy. So we have talked about what is the current like. So this is Q1A, which is kind of representing the current. The radiosity is kind of represent the voltage, and this over here represents the resistance. Okay, so how come this equation is still valid? Well, for one thing, you can see that the view factor from 1 to 2 is 1. So that basically makes this equation f1 to 2 here, that is 1 also. So it will just reduce to this, because basically there are no other surfaces that are available. Okay. Now where this similarity breaks down, this similarity will break down once you have more than one surface. So let's say we have the slightly different analogy. Slightly different case where we have, let's say, 3 surfaces. Okay. So we have J1, J2, and J3, right? Let's say we have this triangular kind of a case. So all of a sudden, okay, we find that, okay, let's say there's emissivity 1, emissivity 2, and emissivity 3 over here. Okay, so what are the equations governing them? So let's try and draw an equivalent resistance network, and how is it being done? Okay, so we'll go through that in this video. Alright, so as we've seen before, there are actually 2 kinds of resistances. Okay, we have not seen that before, but now we'll discuss it. There are 2 kinds of resistances. Okay, let's take a look here. I'm going to highlight these 2 equations. Can you see that one kind of resistance, as if you take a look here, one kind of resistance has to do with the area and the view factor. Okay, so I'm trying to give you an intuitive explanation on that. So let's say you have this surface and this surface, S1 and S2. So the amount of heat transferred from S1 to S2, it will be dependent on the view factor, right? And if S2 is a certain size, the view factor is a certain amount. If I enlarge S2, the view factor is bigger, because the solid angle from S1 to S2, that is going to be bigger. So what does that mean? If there's a bigger surface or bigger view factor, f1 to 2, what does it mean? It means that the resistance to heat transfer from S1 to S2 is much less, right? Heat transfer from S1 to S2 is much less with a bigger f1 to 2. So this is what we call the space resistance. Okay, so this is space resistance. I will put this here. So space resistance, right? If you have a bigger view factor, alright, because view factor will range from 0 to 1. It is a fraction of the total amount being emitted by this surface S1. So if you have a bigger view factor, there is less space resistance. Hopefully that makes intuitive sense. Second one, which may not make as direct sense, but it should still be intuitive, is the surface resistance. Now this is called surface resistance. You see this thing here? Emissivity and area being involved. So let's say we have a gray surface, right? A gray surface, with emissivity equals to 0.9. So let's say it's at temperature T1 or T1. The total heat per unit area, the heat outflow per unit area, equals to epsilon times the black body emission, the black body emissive power. So the total emissive power here, total emissive power from this gray body equals to the emissivity times the black body power, right? We don't include reflection and all these yet, but we might have heard that black body is the best kind of emitter. So, right? So, okay, let's try this. So 0.9 EB. Alright, 0.9 EB is what the emission will be. Of course, then now you have to incorporate this little bugger called reflection as well. So for opaque surface, you'll just use the 1 minus epsilon into HR. Alright, 1 minus epsilon into HR. Alright, so that's where radiosity kind of comes in. So you cannot just consider the emission, but you also have to consider, you know, the reflection that's coming off the thing. Okay, so that kind of offsets the thing. So does the reflection make this this Q bigger or smaller? So we have done all the math before, right? We have done all the math before, and we have seen that, hey, if we have seen this this math kind of play out, and it's kind of settled us in this equation here that relates the black body emission, radiosity, and of course the net heat flux coming out of this thing. So yeah, that's all the math that factors in this little reflection thing. And after accounting into the taking into account the reflection ability, the reflection term, we kind of have this equation over here, 1 minus epsilon over epsilon times A. That becomes the resistance. So okay, that takes into account the surface resistance. So with high emissivity, let's say emissivity equals 1, then what happens to this resistance? Emissivity equals 1 means the resistance goes to 0, because the numerator on top 1 minus 1 becomes 0, right? Then what happens if emissivity approaches 0? That means if the emissivity approaches 0, then you see this denominator going to 0, the resistance goes to infinity. So basically the idea, regardless of whether or not there's reflection, is pretty much the same for this gray diffuse surface. If you have more emissivity, the easier it is for heat to be transferred off this surface. Okay, hopefully that makes sense. And this is called the surface resistance. Okay, this is called surface resistance. I'm going to put surface resistance. Okay, surface resistance. And how can we imagine that? Well, let's say you have a black body here with some black body emissive power, EBT, based on the temperature. And now if you have emissivity, I mean you have actual gray surface that prevents heat from going off, you can imagine putting a layer of shield here. Alright, so the heat's trying to come off this thing, but some of it's getting bounced back by this shield layer. Some shield layer. Okay, you can imagine it like that. So the net heat coming out is a lot less. Alright, because some of it's bouncing back. So this gray surface kind of prevents heat from getting out as efficiently as, let's say, a black body. So the effect of that gray, that lower emissivity, is as if you're having a little reflective shield here to prevent some of the heat getting out. So if you were to think of it like a greenhouse effect, right? Let's say you have Venus, which is extremely, like a greenhouse. It's very reflective on the surface, yes. So it reflects a lot of light from the sun, like the planet Venus. But because of the greenhouse effect in Venus, when there's lots of clouds and everything, it prevents heat from getting on the surface. So it's extremely good insulator. So so instead of Venus radiating like a black body, it emits with emissivity less than 1, and perhaps much less than 1, and that's why it stays very hot. So this is called surface resistance, and it's described by this term over here. Okay. So how does one actually calculate the heat transfer based on these resistances? Okay, so if we want to calculate, let's say, between these three surfaces, the heat transfer from, let's say, 1 to 2. Yeah, so if we want to do between these three surfaces, we'll need to do some simple thing, right? Okay, so this EBT and J kind of represent the voltage. So between these two surfaces, right, imagine there is some, like I said, there's some ideal black body here, okay, which represents the bottom surface as if it were a black body, and the emissivity equal to 1. So it's EB T of the first surface. This is EB 2 T for the second surface. Okay. So there'll be so-called like a resistance between here and here, because remember I was saying this gray thing acts like a shield. Okay, and then there will be a resistance between here and here. Okay, so this will be the space resistance here. Space resistance TANC and CE, and this will be the surface resistance. Okay, so I'm just gonna copy and paste all of this here, and based on this we can kind of calculate let's derive an expression for the heat transfer. So right, at least from this point perspective, it is easy to see what the resistances are, and then we can just say, okay, we have the voltage here and the voltage here. We do not need to know what this J1 and J2 are, and then we can say, oh, we can find out the heat transfer just by looking at this. So let's say you want to heat transfer from Q1. You want the heat transfer from 1 to 2. Okay, so we all have remember the voltage, EB1 T minus EB2 T. That's assuming both of them are at constant temperature. Then we'll need to sum up the resistances. So there are two surface resistance to sum up. Okay. So this is the resistance of the first surface. Okay. No color. Resistance of the first surface. And then the resistance of the second surface is as such. Okay, resistance of the second surface is as such. And then of course you have the space resistance, which is this. this one in the center. So this is the first surface, this is the second surface, and this is the space resistance. So with all these together, we will have an expression for the heat transfer from 1 to 2. Of course, when the surface is I mean, this is an infinite area kind of thing, so if we have the area going to infinity for all of them, we can kind of assume an infinite heat transfer area, which kind of makes this calculation a little pointless. But what is perhaps more meaningful for us is to divide this throughout by the area. So we'll divide the area throughout. So I'm going to get rid of the area here. So dividing by area, you will have an area here in the A1 in the numerator, so you'll cancel. And since A1 equals to A2, there's symmetry, right? Infinite parallel plate, this one can cancel, and this one can cancel, right? And that's to deal with the infinite area thingamajig. Alright, if the areas were not infinite, we won't do this anyway. So anyway, F1 to 2 is, what is that? That's the view factor. The view factor in this case happens to be 1 because all that A1 sees is A2. So basically we have an equation describing the net heat flux between the two surfaces, as S1 and S2, based on the black body temperature and of course the resistances here. Now you can see with this resistance analogy, we don't have to think about the reflection, because if A1 reflects something to A2, okay, if A1 gives A2 some kind of a radiation amount, then A2 will reflect some of that radiation back to A1, and then you keep having reflection back and forth. Calculation is going to be pretty much next to impossible. But with this network analogy and with the inclusion of radiosity and of course cancelling out the radiosity, and even better, using this resistance network analogy, it becomes much easier to calculate heat transfer, or at least the heat flux, radiative heat flux between, let's say, these two surfaces. And if you take a look at the textbook, you can see it's pretty much the same. Look at this. There's what do you call that? Heat flow from EB1 to EB2. Alright. Alright, so this is what it looks like in the textbook. EB1 to EB2, and then you have to cross these three resistances. This is the surface resistance, and this is the space resistance. Now in the next video, I hope to be able to look at a little more complicated problem before we kind of move on to the next thing in the list of stuff to go through for this radiation learning journal, which is participating media, which makes all these things look like a piece of cake. But anyway, thanks for watching. I'll see you guys next time. Hopefully we can do this example.